Good day, everyone, and welcome to today's webinar, Digital Airflow Measurement for Optimizing Combustion in Coal and Industrial Boilers. I'm Ravi Krishnan, Managing Director of Krishnan and Associates, and I'll be your moderator today. We are excited to partner with PROMECON, a leader in advanced gas flow monitoring solutions, to bring you this important session on improving plant efficiency and environmental performance. As coal-fired and industrial power plants continue to provide essential baseload power and process steam, they face growing pressure to adapt to the evolving energy landscape, with increased grid variability and rising environmental standards. The key to staying competitive is enhancing flexibility, combustion efficiency, and emissions control, all of which will be covered in today's session. In today's webinar, we are pleased to have Hans Conrads, CEO of PROMECON. Hans founded PROMECON and has since invented numerous measurement systems used globally across power, cement, and smelting industries. He holds several patents and has authored many papers on gas and solid material flow measurement. Under his leadership, PROMECON has become a leader in advanced gas flow monitoring, and today he will share how these innovations are optimizing combustion and improving plant operations. Before we begin, just a few housekeeping notes. Today's session is being recorded, and a link to the on-demand replay will be shared with all the registrants. Please submit your questions at any time via the Q&A window. We'll address as many as possible during the Q&A session at the end. As with all online events, should we experience any technical difficulties, we will work to resolve them promptly. If necessary, we will follow up with a new live session and share the on-demand recording. With that, it's my pleasure to introduce Hans Conrad, CEO of PROMECON, who will begin today's presentation. Hans, the floor is yours.
Well, Ravi, thank you very much for this kind introduction. I welcome everybody who is now switched on to listen to our presentation about airflow measurement in coal-fired, or actually in in solid fuel-fired boilers, I must say. It's coal firing, but it's also biomass and other sorts of solid fuels that are fired. As Ravi rightly said, in today's world, steam generation, power generation is still heavily dependent upon coal firing, and it will not change in the near future because the power demand worldwide is increasing by new technologies, not only AI, but also by the high demand for mineral processing. All these are really driving up energy consumption worldwide, and coal is available in abundance, especially in countries of Asia, but also across the continent of Africa and other big areas. So today, I'm very happy to talk about our technology. Before we start, let me just introduce our company briefly for those who don't know us. We have been around for 30 years now. We have been founded in 1995. We're located in the city of Magdeburg, not too far away from Berlin, the capital of Germany. And we are actually delivering our technology to the power industry, to the cement industry, waste to energy, and smelters. And what we are really specialized in is measuring hot process gas. And I will go into more detail of what it means to measure hot process gas and why this is so important for your industry as well. Let me give you just a complete overview of the industries that we're working in. It's the power generation, waste to energy. Then in the steel and iron making, we are into BOF, EAF, but also sintering and dedusting of plants. Then very big part of cement making and limestone. And then, of course, the whole non-ferrous sector, lead, zinc, copper, whatever, you name it. So it's a very wide field where we are active. The three biggest market segments that we have been serving, you can see here, which is power, steel, and cement. You can see the main the main markets for us has been Europe and North America, but also South America, Africa, and Asia are now becoming very attractive markets for our technology. Today, I'm talking about digital drift-free vector airflow measurement. And I think before we go on, we really need to recap a little bit on these three words: digital, drift-free, and vector. All three things are very important for your process, and I will explain why. Before we do that, let's just have a quick look at a boiler. Boilers are very large machines. They're probably one of the biggest machines for energy conversion that I know. You can have boilers up to 100 meters tall, and these boilers are very prone to maldistribution of the airflows, which is used to combust the coal. So you have a huge boiler, you measure your O2 at the back end, but what does it mean for the combustion chamber, which can be big as a large room? You have 20 burners, several burner rows, and the air distribution across the burner rows is very uneven. And with that come all the problems that you have in combustion. High CO, at the very same time, high NOx, maldistribution of heat, pipe leakages, slagging, eyebrows, flame impingement, you name it. I mean, all the issues that you have in your boiler come from this problem. Even if you have clinkering coal in the bottom of your boiler coming from your mills, it can be as simple as a primary airflow problem because the coal is not pushed through your pipes in sufficient velocity, right? So all the issues that you have in your boiler are driven by air maldistribution. So what we offer is proper airflow for the primary air, proper airflow for the secondary and OFAR, proper airflow measurement for IBFM, for individual burner flow measurement. And then, of course, we also can measure the flue gas downstream of the boiler and downstream of the air heater. So we can measure flue gas in and out of the ID fans. We can measure flue gas into the scrubbers and into the stack. So the total airflow and gas flow measurement spectrum is pretty wide, and it helps you significantly to optimize excess air reduction, unburned carbon reduction, slagging problem reduction, and so forth. If you can manage your airflow better, let me just tell you this much: you can save up to $1 million worth in fuel every year. $1 million savings per year if you manage your airflow better than you do it most of the time. So the next question is, why do people have such a problem with managing their airflow correctly? Well, the big issue here is that your airflows that you are measuring are usually measured by a delta P device, a so-called delta pressure measurement. And before we look into that and the problems, I would like to point out how the air and the process gas is processed in your plant. I mean, everybody knows it, but it's important to look at this example again. All of the large boilers usually have a rotary air heater. The rotary air heater is basically shoveling the heat from the flue gas back into the fresh air. So a big portion of the heat that you would lose on the flue gas is put back into the fresh air stream by the rotary air heater. The rotary air heater is a big carousel. It contains a lot of metal plates with a thermal mass. So if the hot flue gas goes by these metal plates, it heats them up. And as this rotary air heater is slowly rotating like a carousel, the hot plates finally reach into the cold zone where they lose the heat again, and the cold fresh air is heated up. During that process, the metal plates also agglomerate ash. So they are full of ash. And as the rotary air heater turns into the cold air zone, this ash is released, and therefore the ash is flying through the ducts now as preheated air. So the preheated air always contains ash originating from the rotary air heater. And as you can see, it has nothing to do with the leakage of the air heater, because the leakage goes from the fresh air side to the flue gas. so from the pressurized to the negative pressure side, whereas the ash goes the opposite way. It simply goes always from the flue gas into the fresh air side. So what you have is airflow with ash. And in some markets, such as India or South Africa, you have quite a lot of ash in your air because your coal contains so much ash. You can have coal with ash content of 30–40%, and then, of course, you have a lot of ash in your air. But even with coal of lower ash content, you will always end up with ash in your air. What happens? If you look at this is a typical airflow device, like you see it in hundreds, if not thousands, of coal-fired boilers around the world. It's an obstruction, in this case it's a venturi, but it could also be an airfoil, it could be an orifice, some obstruction in the duct which will create a pressure drop. And this pressure drop is then subsequently measured by a DP transmitter. So you have a venturi, for example, or an airfoil. This creates a delta pressure, and you measure that delta pressure by two impulse lines, one impulse line before the venturi and one inside the venturi or inside the airfoil. The delta pressure is not very large. It's about 20 millibar or a few inches of water gauge. So we're talking here very small pressures. Now, why is this important? Well, you take this pressure and according to the law of Bernoulli, you take the square root of the pressure and that is proportional to your flow then. And you put this value into your controller and the controller then controls the louver dampers so that your set point of airflow is reached. So somebody puts in a set point, let's say 25,000 norm cubic meters per hour, and then the controller looks at the DP measurement and it calculates the flow, and then it changes the louver damper until the correct flow is reached. And that is a very important point because that prevents the operator from seeing whether the DP transmitter is correct or whether it's drifting. An operator cannot see that because the controller will always correct the flow value to the set point. Now, why should the DP transmitter drift in the first place? Well, look at this. You could have the dust that we're talking about from the air heater clogging up your impulse line. In this case, the impulse line will be blocked. So the pressure will not get to the DP transmitter any longer unhindered. You might have certain blockages that will prevent it. Now the question is now, we have measured a delta P. We have measured the difference between leg 1 and leg 2, between impulse line 1 and impulse line 2. If we block one impulse line, what are we measuring? And we have to look at this. This is actually the barometric pressure of your power station. If your power station is at sea level, it's about 1,000 millibar. If your power station is high up, like in South Africa, you have power stations in the Highveld at 1,800 meters above sea level. Of course, it's lower. It's only going to be 860 or 880 millibar. But still, this barometric pressure is huge as compared to the delta pressure that you're measuring. And this is the thing. Any change in barometric pressure will now run one-to-one against your DP measurement. Yeah? So you will not only see a wrong measurement that is locked up, but you will see a measurement that can also be drifting. If you have a thunderstorm coming up, your barometric pressure can go down by 10 millibar, which is already 50% of your full range delta P. Yeah, that's the problem. You have a delta P transmitter, you clog up one duct, and then you will start to drift. And as I have explained before, your operator cannot see this. Your operator, it's impossible for him to see it because the controller of your plant will always control the louver damper to the set point. Let me show you an example how this looks live with live data. This is a trend from a power station in Germany. It's a power station located in the city of Berlin. The 2 units, 360 megawatts each, coal-fired, wall-fired. And what you can see here is the flow measurement of one secondary air duct. going to the burner. The dark blue line is that DP measurement. And you can see in the middle of the picture, somebody was cleaning the impulse line. So somebody went along and blew it out and cleaned it. What you can see before and after the cleaning is that the noise in your measurement goes away. So before cleaning, it's noisy measurement. After cleaning, no noise. So what you see is that the level of the measurement has remained the same. You are seeing 25,000 norm cubic meters before cleaning. You are seeing 25,000 norm cubic meters after cleaning. What's the problem? The problem you can see below. The light blue line is the air damper position. And also here, before and after cleaning, the noise in the air damper sharply reduces. You have a very quiet air damper after cleaning. But something different is happening. You can see that the air damper is changing position before and after cleaning. It's not the same. That means the airflow before and after cleaning cannot be identical. It must be different. So what the operator sees in the DP measurement is simply not true. The DP measurement is wrong. Before cleaning, the DP measurement was showing a value that was too low. And you can see it in the change of the damper settings. So obviously, the operator is seeing something that is not correct. Yeah? Let me show you another example. This is the power station, also in Germany. It's an Alstom boiler, 800 megawatts, ultra supercritical, 620 degrees Celsius, live steam temperature, fairly new. What you can see here, the red line is your DP measurement. The cleaning you can see about 2/3 to the right. And again, you can see some noise shortly before the cleaning, and after that, the noise is much better. But before and after cleaning, the level of the red line, the level of the delta P measurement is the same, no difference. If you look at the blue line, however, the blue line shows you the air damper position before and after cleaning. And of course, you can see here, the damper has changed position. So again, the same thing. The operator cannot see that the delta pressure measurement is drifting, and it has been drifting long before the cleaning. You can see days and weeks and months of wrong delta P measurement without the operator noticing it, because the measurement always sits on the set point. What you can also see here is the yellow line. The yellow line is a parallel measurement of PROMECON, our device, which is not drifting. And you can see that the yellow line follows very nicely our damper position. So our measurement is not drifting away. It follows the damper all the time because our measurement cannot drift. Okay, that was problem number one. What you can also see here is the typical noise that I was talking about. The noise is basically a resonance between the flow measurement and the damper. Here you can see damper and flow measurement in both trends. And if you really look close up, you can see that the damper and the measurement dynamics is about 90-degree offset, which is basically a perfect resonance condition. So what happens is the flow is too low, the DCS system opens up the damper, the measurement does not follow, so only after some time it follows. It is because it's blocked, the impulse line is blocked, so it takes some time for the air to reach the DP transmitter. And then the DP transmitter overshoots, and then the damper overshoots. And so it goes back and forth. It's a perfect resonance, as you can see here. So with our measurement, you don't see this, you don't see any drift, you don't see any blocking, because our measurement does not have this problem. Before I tell you how our measurement really works, I would like to point to another problem that you have. The other problem that you have is the vector, basically actually the swirl that you have in your measurement. I was talking about the fact that our system is a vector measurement instead of a scalar measurement like DP. What is this problem? You can see here a manifold, and this manifold shows you that you have the air basically coming towards you in this lower rectangular blue, dark blue section. The air comes out of the screen towards you. And then in the middle manifold, the air simply turns upwards. So it's a 90-degree bend. And you can see no swirl. But the two manifolds, left and right, they are not just turning the air up, but they're also turning the air sideways. So the air is forced sideways and upward. And if you do that, the air has to fulfill sort of a screw type movement. Now, since the air has a mass and it has an inertia, it doesn't want to do that. So therefore, it simply goes in a straight line, which results in a counter screw movement, right? So you have in both ducts a swirl, pretty big swirl. Now, the outer ducts do not have this big swirl anymore. So to put a long story short, in every duct, you may have a swirl or you may not have a swirl. You simply don't know it. And therefore, you cannot calibrate for this. And your delta pressure measurement will not detect the swirl. It would simply give you a wrong reading. Also, other devices such as thermal mass flow meters or whatever, they will give you wrong readings, and you really will have to guess on what the true value is. Our measurement does not have this problem. Our measurement measures the true propagation velocity of the gas in your duct, and it will not see any lateral movement or any swirl component. That's a huge difference to any other measurement on the market. So now that we're finished with all the problems and why they are around, let's see how our measurement is overcoming these problems. What does our measurement do different in order to overcome these problems and work properly? Well, first of all, you can see that our measurement has two sensors. We're not measuring the velocity with one sensor, but we're measuring with two sensors that are at different locations. And you might already guess, two sensors, different locations. Well, there might be a vector involved between the two. But before I go there, let me explain the measurement principle. The measurement principle means that we use two physical things to calculate the flow. The first one is we use an electrostatic signal which comes from the dust in your duct. So the dust that I have described as the enemy of all delta P measurements, of all thermal anemometers, this dust is our friend. We use this dust as a tracer, and we use the electrostatic signal that the dust creates on our sensors. And the second principle is that we correlate the signal that we get on two sensors in order to calculate the time of flight between sensor 1 and sensor 2. That's basically how we do it. Let me explain further. Here you have our sensor in the duct. You can see the antenna reaching into the duct. Now, in the duct, you have particles which are charged. These charged particles are basically the charged ash particles coming from your air heater. So they can be positively charged, they can be negatively charged. In any case, in the vicinity around your sensor antenna, you will have different electric fields. Sometimes they are high, sometimes they're a little bit lower. And this is a function of the clouds of particles rushing by your sensor. So what you can see down there is basically the opposite charge on the antenna. You remember Coulomb's law from the physics lesson. So we have the opposite charge changing over time. What we see then is an electric current over time. And this electric current is basically the fingerprint of the particles flowing by the antenna. Let me show you more. If you have more particles, we have more fingerprints, right? So basically, as the particles rush by, we can measure this unique fingerprint on one sensor. Now, the next step is that we take two sensors. We have two sensors that are spaced about 300 millimeters, and they are oriented in the direction of flow. So we have an upstream sensor, and we have a downstream sensor. Now just think about this. You have two impulses, impulse 1, impulse 2. You can see this in the two graphs. If you do a cross correlation of these two impulses, you will get a cross correlation function. And this cross correlation function will show you the time shift to the maximum overlap of these two impulses. Let me show you this, how this really works. Of course, in reality, we don't see a single impulse, but we see a succession of impulses. We see a succession of clouds. But the thing is, since they are erratic, they are really random. So we have a random fingerprint, And if we put these two sensors, which are closely spaced, 300 millimeters, if we read out the signature of both, you can see they are very similar because they are not very far apart. However, the overlap is very low because they are time shifted, of course. Sensor 1 is earlier than sensor 2. So what we do now is we put them into a cross-correlation filter, and this filter simply shifts the two functions towards each other in a digital form. And it just measures the overlap. And if you keep on doing that, you will see that there is one time where the overlap is maximum. This time is basically the time shift between the two functions. And it's identical with the time of flight of the particles between sensor 1 and sensor 2. So this is the time of flight of the gas between the two sensors, right? So you can see, for example, here, sorry, let me mess this up a bit, 52 milliseconds. So what we have now is we have a time of flight between two sensors. We have a distance of the sensor of 300 millimeters. So if you divide distance over time, you have meters per second. And what you do now is you simply take the cross-sectional area of the duct, square meters, you multiply square meters times meters per second, and you get cubic meters per second. So it's very simple to arrive at the actual flow. Now, how do you get finally to your STP flow, to your standardized temperature pressure flow? You simply compensate for temperature of the gas and for barometric pressure. And that's it. So with a very simple time measurement, you arrive at a digital flow. And as you can see on the slide, this flow will never have to be purged and corrected and recalibrated. The calibration of our system stands over the life of the system. If you put the system in a cement plant, in a coal-fired power station, in a steel smelter, the system will continue to operate throughout its life with the same calibration. So there is no recalibration. And also for normal power station measurements, you don't have to purge or clean the sensor. And I will show you this in an example. Look at this sensor. This is from a cement plant. You can see here on the lower right-hand picture, we pull one sensor out. That's how bad it gets in a cement plant. This is not as bad as, it would not get as bad in a power station, but even in a cement plant, the drift of the signal is zero. There is absolutely no drift. Again, why is there no drift here? There is no drift because we don't care about the amplitude of our current that we measure. The only thing we care about is the change over time. So we only care about the time pattern and how quickly it repeats on the second sensor. And for that reason, it's a purely time-based measurement. It's something that would never be influenced by the amount of ash sitting on our sensor. And that's the big strength of it. It's digital, always accurate measurement over the life of the instrument. Now there's more, of course. I promised also the vector thing. If you have swirl in a duct, actually your gas flow is not going in a straight line, but it can swirl, it can have a lateral component. You can see here the orange line, which is not going in a straight line, but it's just offset. Now, as I mentioned, we measure time. We measure a time difference between sensor 1 and sensor 2. And you might ask, well, time is not a vector. Time is just a scalar value. Yes, but you remember, we divide the distance of the two sensors over time. And distance certainly is a vector. What distance are we assuming? We are assuming the distance that is basically the vector perpendicular on the two sensors. You can see the blue vector down there. That's the distance that we are calculating. So even if we have a lateral component, like in the orange vector here that you can see, the distance that we're calculating with is the vector between the two sensors. And for that reason, any swirl will not affect our measurement. Take a look. Here you have the darkening. Yeah, you have a typical swirl. And the swirl will also go have a lateral component between the two sensors. But what we see that the air is moving upwards, and we can detect the same statistical pattern on sensor 2, but we then only divide by the vector that is orthogonal or perpendicular on the two sensors. And for that reason, the swirl component is simply not seen. And that is another very big advantage. Okay, that brings us to the end of the working or measurement principle. There's one thing I would like to add for you as power station people. You might have asked yourself, what if I don't have any dust? I mean, everybody of you knows how to start up a coal mill. And if you start up a mill, you are also using cold air, right? So you open up your cold air damper. There's no hot air, just cold air in order to purge the mill, to start the mill up. The cold air is not going through the rotary air heater. So you might have cold air that is not carrying a lot of dust. The question is then, if I don't have any dust, how can I then make this cross-correlation measurement properly? The answer is the range extender. We have invented this and the patented system to be able to ionize the air that passes by this range extender. And we do this with a small high voltage pulse. It works a little bit like a spray electrode in an electric precipitator. The only difference is that the power levels we need are very, very small. They are just milliwatts. But these small ionizations of the air, they will subsequently be going over the two sensors. And on the sensor, they will also leave a blip. Let me call it a blip. Yeah? You can see it on the right-hand side. You have the electric pulses on the left-hand side, 3 spikes. And on the right-hand side, you have 3 blips that you can see. Now, if you have 2 sensors behind each other and you cross-correlate these blips, you can see here the red and the green. These are the 2 blips. First sensor, second sensor. And the cross-correlation of the 2, again, is the blue cross-correlation. Very sharp, very distinct, and we know exactly the velocity. The range extender has 2 big advantages. That's why we also call it range extender. First of all, it extends the range of dust that we can measure down to absolute 0. So we can measure now high dust levels, and if there's absolutely no dust, we can still measure. We will always be able to measure. The second thing is that the electrification of the dust is also depending on the velocity of the gas. So when you have very slow gas below 8-7 meters per second, the electrification gets very low and the cross-correlation is harder to find for the system. The range extender changes that because the range extender always provides a constant ionization of the gas. And so the range extender also extends the low velocity range of our measurement down to 3 meters per second. And that's very significant because now you can measure very slow airflows. For example, you switch off a burner row. You only have cooling air going into this burner row. Now this cooling air is very, very slow. With a delta P device, it's impossible to measure. Let's say your cooling air setting is 10% of the max flow. If you want to measure this with a delta P device, well, you have 10% of the flow, which means you have to measure 1% of the delta pressure. Because according to the Bernoulli equation, that is the square root of the pressure is the flow. So you have to detect 1% of your full-scale range, which is, I think, utopical. It's very hard to do. With our measurement, it's a time measurement. What happens if the air gets more slow, if we have a slow gas flow? Well, then the measured time difference goes up. So the lower the airflow, the larger the time difference becomes, and therefore the higher the resolution of our measurement. So you can safely say that even very low velocities are measured very, very accurately by this technology. And that is another big advantage for you in the measurement. So here you can see a range extender, how it looks like, typical. It pretty much looks like a sensor, and you put it upstream of the two sensors, and it runs completely autonomous. It has not connected to the sensor whatsoever, just keeps on marking the gas flow all the time with the ionization. So let's have a look. How does the system look like? This is a typical one-channel measurement system. You have the measurement box, you have the two sensors, and the measurement box takes in the power supply, it takes in the raw signals from the sensors, and out comes your 4 to 20 milliamp signal that is typically then sent to the plant. Here you have the full setup with a range extender and a temperature measurement. Usually we recommend that you do the temperature measurement separately and put it directly into the DCS, and you do all your compensation in the DCS because that makes you independent of the specific location. But whatever, if you want to compensate the temperature directly in our box, it's also possible. That's really a setup of how you want to integrate our system. But important message is 4 to 20, very simple. You integrate it the same way that you integrate your delta Ps. So just to sum up the main reasons for measuring, the main problem that you have is drift. All of your measurements drift and your operators cannot see it. You may have sometimes mill trips, and that's when you measure it, but it's usually hard to see. On the secondary air, the OFAs, the SOFAs, all these airflows are hard to see whether they're correct. If you have our measurement, you can be sure that the OFA, SOFA, and secondary airflows are measured correctly, and you will not have to climb up the boiler every year and check for the correct flow. Our measurement is digital. It will never drift. That's the main advantage of it. And then, of course, all the other ones I've mentioned afterwards. Well, let's look at how this system is integrated into a typical plant. Here you can see that's the Alstom boiler I was talking about. It's the new Alstom boiler, 800 megawatts and all the bells and whistles. In this boiler, they had all Venturis. You can see this Venturi on the right-hand picture from the outside. These Venturis were drifting all the time. You can see this rather, this 45-degree duct sticking out. That was a cleaning duct in order to purge this whole thing, to keep it clean. It was all not working well. So they finally replaced this delta P measurement with our digital airflow measurement of PROMECON. You can see here the box, you can see the sensors, and you can see the range extender. The other picture on the left-hand side shows this duct from the inside. Here you can see the Venturi and how the sensors stick in the duct and how they measure. They have replaced all of their primary airflows, secondary airflows, overfire airflows with our measurement. Here another plant, it's a Mitsubishi Hitachi plant in Germany where the sensors came in from the start. They still built in a Venturi because they wanted to be sure they can replace our measurement with something else if it doesn't work. This is station Walsum. It has been working now for plus 10 years and the customer is extremely happy. The whole power station is controlled by our measurement and nothing has been ever replaced by something else. Here you can see another example of a flue gas measurement. We have done total flue gas measurement on these boilers in order to optimize the ID fans and to check the efficiency improvement. You can see how this looks, total gas flow measurement out of the boiler. This has also been done in other plants in South Africa, in Asia, and this is also a very important part of the checking of the distribution of your airflows. Some people in the US have done this on their flue gas duct in order to measure the distribution of the flue gas into their scrubber units. So they have, let's say, they have two boilers, they have three scrubber units, and both boilers feed into the three scrubber units, and they simply wanted to see how is my flue gas distribution and how can I control my scrubber in order to optimize my operation. Yeah, and this brings us to the typical certificates. We offer this measurement normally with the conformity of technology CE certificate. We also do have an SIL certificate. So some boiler operators in Europe especially, they want to have SIL2, Safety Integrity Level 2 rating. And our systems are rated SIL2. So for boiler safety, if you need our systems for boiler purge and boiler startup, this can all be done using our systems, and the SIL rating is also part of our system. I would spare a little bit of the details. I would spare that for later if you have more questions. Typical setup here, you have a single box with a typical IP66 or NEMA 4 ratings. And here, different sensor types that you can go in. We'll be happy to provide this to you. So that brings me basically to the end of our presentation and to the Q&A session. I'll be happy to take your questions. Thank you very much.
Thanks, Hans, for an excellent overview. As we move into the Q&A session, you'll notice a pop-up box appear on your screen for about 2 to 3 minutes. This will give you the opportunity to request a one-to-one deep dive session or a custom presentation tailored to your broader team. You can also invite colleagues from areas such as plant operations, planning, or boiler or combustion performance to join the discussion. So simply click your preferred option, and the PROMECON team will follow up by email to schedule a convenient time. At any point, you can also drop us a message through the Q&A widget as well. So you have a couple of different options to reach out to us. So let's start with some of the questions that have come in. We have a number of questions from the audience, and we'll try to get to as many of them as we can. So Hans, one of the fundamental questions, and perhaps a reiteration, and the questioner is asking, how can I determine whether my plant has inaccurate airflow measurements?
Yeah, that's a very good question, and I've mentioned that it's very hard for the operators to see. There are some culprits when it comes up to the operation of the plant that you can identify. For example, when operators tell you that they like to take the mills on manual, or they like to take any damper on manual because of vibration and because of process noise, because the mill is running more smoothly, that's usually a very big hint to the fact the mill does not have a problem. It's the airflow measurement that has the problem. And how do you detect it? Well, if you have, let's say, 6 mills running, it's fairly simple. If you feed the same coal to the mills, what you do is you get the instantaneous value for all 6 mills of coal feeder, PA flow, temperature in, temperature out. If you have these 4 values, coal feeder, PA flow, temperature in, temperature out, you can calculate how much enthalpy of the air is used up per kilogram of coal for drying the water. And this number should be very similar on all 6 mills. If you have vast differences, then you can be very sure physics is not different in these mills. Physics is always the same. Some of the values that you have punched into your equation are wrong. And most of the time, it's the airflow that's wrong. So you can do this, mill mass energy balance. The other thing you can do is you can print out the trend of your secondary airflow, your OFAS, and you can put the damper trend right next to it. I've shown these pictures. For example, you can see this here. Let me just jump into that. Yeah, you can do this same thing. You can look at the damper trend and the DP trend. And if they are not consistent, if the dampers have they're moving in a different way than your DP flow is moving, you have a problem. That's already the proof that you do have a problem. So that's the way you detect it. That's usually not done by operators, but if you're a boiler engineer, a performance engineer, or you're a measurement guy, you can get these screenshots. You don't even have to go to the boiler house to detect it. You can just take the screenshots, or you can just take these screenshots and send them to PROMECON. We will do the analysis for you. It's not very hard. So if you have a typical mill problem, send the screenshots to us. We'll do that. So.
All right. The next question is, what is the recommended maintenance interval for your system, and what does routine maintenance involve?
Yeah, as I mentioned, delta P devices drift. Our systems do not drift. So there is no regular recalibration and also no regular cleaning necessary for our system. We have many customers that don't look at our system for years. Of course, we do not recommend that. If you have a boiler overhaul, it's always good to send someone out to look at all the sensors. Are all the cables intact? Is there any issue? Are there any sensors bent or damaged by somebody? Also to pull out a sensor and see is it still, is there no excessive wear on the sensor? Usually these sensors do not wear. They don't wear within 10, 15 years. And even if you see slight signs of wear, the impact on the accuracy is nil. It's zero. But you should have a look at some of these sensors. And usually when we have people running a boiler with 20 measurements, every now and then we get a request to send them 1 or 2 spare sensors to replace this and that. So that is the typical thing. So there is no regular maintenance every week, every 2 weeks that you have to do. If you have a SIL sensor, then the procedure of SIL requests you to do a so-called proof test every 2 years. So you have basically to prove that the system is internally intact. That is an automatic procedure. You cycle the power on the instrument and push a button, and then you just see if it comes back on after 10 seconds. It's okay, and you note that down. So it's a very simple procedure for SIL. So that's all I can think of.
All right. All right. Another question from a power plant operator, presumably who has some biomass blending or co-firing with the coal. The question is, does airflow measurement performance remain accurate when biomass pellets are coal-fired with the coal?
The simple answer, yes. They have this. You have ash coming through. You have the accuracy levels simply do not depend on the type of fuel fire.
All right. What screenshots or data points are required to verify the correctness of airflow measurements? Also, how can we accurately provide you this information? I guess that's a communication issue.
That's a repeat.
Yeah.
Screenshots of filling plants. I've mentioned that. So if we get that, we can help.
Okay, great.
I used to see another question, which I found there are many interesting questions here. We cannot answer them all, but one interesting question, which I found fundamental. Somebody asked, how much straight length do I need for this? This is a very good question, very important question. Power station ducts are all big in cross-section, and they never have long straight runs. But the good news here is that in most of the power stations that are existing, you do have existing flow measurements. You have aerofoils, you have venturis. So you do have existing flow measurements where the duct is tapered down to a smaller cross-sectional area. And this reduction in cross-sectional area increases the velocity at the measurement point. Of course, you want to have a TP. For our measurement, it's a very good point to take a measurement because all these, the aerofoil gaps, the venturis, the orifices, anything that narrows down the pipe acts as a flow straightener, right? So if you are behind a bend and you have a flow profile that is stratified, as soon as it hits the venturi, as soon as it hits the airfoil, it will be rather flat and it will not be stratified. So using these, we can go fairly close to bends. The usual procedure is that people send us a boiler picture and typical duct routing, and we can give them a recommendation of where to go. Usually there's always good locations in a boiler to go, but you have to make sure that it's done the right way.
Mhm. We have another question regarding the bending of the duct and how it will impact the flow measurement. Is that something you can expand on, Hans, for the questionnaire?
The bending of the duct.
Yeah.
Yeah, well, as I just mentioned, it's important to see the routing of the duct. If you have one straight duct, then of course you have to keep on certain distances. If you can't, you have to use several pairs of sensors to make an average of the cross section. But I must say, in most power applications that we have seen so far, this is not necessary because power boilers always have existing flow devices such as aerofoils and venturis that you can use to measure, and that's usually done. It's usually a very good measurement location for us.
Okay. What about the ash deposits on the sensor tip portions? How do you clean those online?
You don't have to clean them. The ash is a dielectric material, so the electric field of the other particles will still go through the ash into the antenna. And as I mentioned, even if the ash has a certain dampening or certain attenuation effect on our current that we are measuring, please be aware the amplitude of the current is of no meaning to us. The only thing that is of meaning is the change of the current over time. This is really the time dynamics of the signal is what we measure on point 1 and on point 2. And the time dynamics tell us something about the time shape of the signal. And the time shape is like a fingerprint. It's what we call time signature. And if we measure that on sensor 1 and sensor 2, the time signature on two sensors close to each other is very similar, but it is time shift. And this time shift is what we measure. So we don't care about the amplitude of the signal. We only care about the time change of the signal. And therefore, ash deposits are simply irrelevant. We don't clean ash deposits. We just leave them on the sensors forever. They blow away over time. Sometimes they're big, sometimes they're small. For the measurement function, it has no impact.
Mm-hmm. Another question around CFBs. Can we measure CFB combustor flue gas distribution, temperature 900 degrees Celsius?
Yes, I was jumping over this, but we do have a model of our system available, which looks like this. This is called the IR, the infrared. And we usually use it in the steel industry to measure the exit gas of electric arc furnaces, which has a temperature of 1,600 degrees Celsius, right? So with this measurement, we can measure easily hot gases up to 1,000 degrees or 1,200 degrees. So the answer is yes. If you have a CFB and you would like to measure the recirculation air or gas at a high temperature, we have the right equipment for that as well. But it doesn't work with a electrostatic measurement. It works with the infrared intensity measurement. But the rest, the cross correlation and all the rest of it is the same. So it's also digital, drift-free, no recalibration necessary.
Okay. Is this measurement accepted or approved in PTC codes during performance guarantees test?
No, it is not, but the measurement can be easily cross-checked with a grid measurement, for example, an S-pitot or a normal pitot grid measurement as specified in the relevant codes. So you have ASME codes for correct grid measurement. In Germany, you have VDI guidelines for that. And in the power stations that I mentioned, the German power station, Belgium, Dutch power station, we have been tested against these grid measurements according to the norms and standards. So our measurement can very well be compared to the norm, but as a big contrast to the norm, if you leave our measurement running then for weeks, it will always be accurate. And especially for acceptance tests, this is very, very important. Gas flow measurement is one of the biggest black holes in performance testing.
All right. Another question from the audience. Okay, what is the maximum temperature range that can be measured?
The sensors that we have are usually, we call them the tactile sensors. These are the electrostatic sensors. This is on the cold side, go usually up to 600 degrees Celsius. And above that, we have the infrared sensors, which go up to, as I mentioned, 2000 degrees Celsius. So hot temperature and dust is not a problem for our sensors. Both is what we specialize in. So for your duct and your application, there will be the right sensor. We also had sensors that go up to 1000 degrees with the electrostatic. So there are special solutions, but the normal thing is everything up to 600 degrees is this one, and everything above is infrared.
Another question from the audience. Since you're talking about solid fuel furnaces, could you describe the measurement method for PF flows?
For PF flows? Well, for PF flows, we have the same cross-correlation measurement that I have already explained, so there's no difference. But in our PF measurement, we also have a microwave measurement, which measures the dust loading of the duct using a resonance frequency. So we use the duct as a resonator, and depending on the resonance frequency, we know how many grams of dust are present in a certain length of pipe. So it's a bit too short in time to explain that. That's another presentation, but I would be happy to answer this question in more detail in another presentation, or we also have webinars and videos on that. Or if the customer wants to write to me, we can have a direct discussion.
Mm-hmm. Another question from a power generator is there any solution for ash flow measurement in pneumatic conveying systems through CI pipes?
Well, for the velocity, I think, the ash transport, it really depends if the transport that you have is a lean phase transport or if it's dense phase. If it's lean phase, your ash has a certain velocity, and you can measure that velocity the same way that you measure it in the airflow ducts. And you can also make a resonance measurement on the amount of density of the ash. So yes, in this case, the ash measurement would work very similar to the co-flow measurement. However, in many plants, due to the high wear of the ash, it is usually transported in dense phase. The dense phase means that you have really a plug of ash, and then you have a little bit of air, and this plug is slowly pushing forward through the duct. And in this case, you don't have a two-phase flow. It's something completely different. So if you have a dense phase flow, in this case, our technology is not applicable.
Mm-hmm. Another question around barometric pressure. How important is it for measurement?
The barometric pressure, you just look it up on the map. If you are on the high mountains, you have a barometric pressure of, 700 millimeters, 700 millibar. It's unusual. Sometimes maybe in Peru it can happen, or in high veld you can have maybe 1800 meters. If you're sea level, you're 1000 millibar. Is the millibar important? Yes, it is. Maybe a little story here. On my first trip to South Africa, I had to calculate the boiler efficiency on a boiler in an old power station, and I was unable to match the numbers. It was impossible. The boiler was way too big, and it all didn't match up. And an old engineer grabbed me and said, "Look, you are on the high veld. Are you aware we are at 1800 meters? We don't have 1000 millibar. We only have 880." And when I put this number in, it all matched up very well. So yes, you have to know your barometric pressure, but please, you don't have to look at weather. Whether you're 880 millibar or 885, that is really not mattering a lot. It's not, but whether you are 800 millibar or 1000, that's certainly a difference that you should look at.
Mm-hmm. All right. Another question around pitot tubes. How do you compare the results with physical pitot measurement using S-type pitot grid measurement?
Yes, very good. You make an average profile, and again, most of these ducts, if you are, for example, inside a Venturi throat, you have a very plug type flow profile. It's really a flat profile or the high velocity, and you don't have much variation over the of the cross section. And in this case, you just take the average reading of your pitot and you compare it to the reading of our system. That's pretty much it. So yes, you can match them. We also had, sometimes clients that we like to, there was a slight deviation between the pitot grid and us. In this case, yeah, we can adjust it slightly. So we have, let's say, a couple of % adjustment up or down. But after that, it would be locked in and it would always stay the same. There would be no difference.
All right. Perhaps you answered this, but I'm going to pose it again just in case. How do small probes function accurately in very large ducts?
Mm-hmm. That's a good question. The first thing, again, is the flow profile. It's very important that you have a flow profile that is overly stratified. If you have, for example, we have done big measurements of flue gas in ducts in large boilers. In this case, we don't use 2 sensors, but we use 8 or 16 pairs of sensors. So we have, and they are very long. So we're using multiple sensors to make an array of measurements of 8 points or 16 points, and then we are averaging them. It's like a pitot tube, like a pitot grid. So we don't have one measurement, but we have many measurements. But if you have a mill and you have a nice venturi, and inside the venturi the measurement profile is very flat, we don't have to worry about it. We put one pair of sensors in, and that is then working very well.
All right. There is some questions around the straight length requirement for the installation of the airflow meter and how the error will be minimized due to if it is short and straight length or any correction factor.
Okay, this question is so fundamental that I cannot answer it completely, but just a few considerations here, please. If you have an elbow, then after the elbow, you will have a stratified flow. How much stratification you will have will depend, of course, on the viscosity of your gas and on the dimensions of your duct, right? So if you have, for example, very cold air, very dense air, you have a different stratification than if you have 400 degrees Celsius hot air. If you don't have a straight run, but you have a tapered section, as I mentioned before, aerofoil or venturi, then all of a sudden the stratified flow will be straightened out and you will have a very, very flat profile inside these locations. So what we do if we have a large installation, we ask the client to send us a drawing of his duct, and then we make a CFD, a computerized fluid dynamics calculation, where we put in the temperatures of the air, if there's any mixing point, that is a complication, and then the geometry of the duct, and then we make a calculation of how flat the profile will be at our location of measurement. If it's fairly flat, we'll use one pair of sensors. If it's not fairly flat, we recommend an additional pair or 2 additional pairs of sensors to average the flow correctly. And all this can then be verified with a pitot tube measurement later on, a grid measurement as specified in the standard, to make sure that our measurement is sufficiently accurate.
Okay. There is another question from a CFB plant operator in India. Mm-hmm. Is it possible to measure limestone flow with PSD below 1 millimeter into a CFB boiler?
The limestone flow, we had this hydrated lime question from people in order to mitigate the NOx and other things. It really depends, again, whether you have a lean phase flow or a dense phase flow. With a limestone injection, usually you have a lean phase flow because the limestone needs to have enough impulse to go really deep into the boiler. So I would say, yes, we can measure the velocity of the lime. The density of the lime, that is a bit of a tricky one. I remember some applications from the past where the lime was sticking on the inside of the duct. So some of the lime is not flowing, but it sticks. It's a very sticky material, especially hydrated lime. So in this case, you have to see that you have a clean measurement section. It's a bit more complicated, but the injection velocity should not be a problem.
All right. We have another question from a power generator in Australia, and it's a long question, so I'm going to try and paraphrase it. Uh, Given our very short, highly turbulent flue gas ducts, where OFS 2000W failed, what minimum duct length and placement criteria does your flow instrumentation require to work reliably? I think I paraphrased this right. She has also highlighted some of the problems she had with other systems. So if you can just expand on that, if this appears to sound clear to you, Hans. Yeah.
Just a quick question. What is OSF 2000? Is it like a device measuring?
Yeah, let's see if the questioner answers that. Put back in the chat, but it looks like it's a general term, like a thermometer. Sounds like it's like a specific model name of a flow meter or instrument.
Well, I can only guess. I mean, we've had some companies try to measure cross correlation with, for example, with laser beams. Yeah.
Mm-hmm.
And this usually doesn't work very well. And the reason why it doesn't work very well is simply that you are looking at very small and local patterns. So you basically look at, a very tiny section of like a cube millimeter. Yeah. And if you have another laser that's a little bit further away, this very local variation cannot be seen on the other laser. Our sensors are much different. We sense the electrostatic charge not only on our antenna. You have to understand that the electric field of a particle or of a line goes down by 1 over distance. So if these particles are further away from our antenna, they will still be seen. And we have usually a volume, an area about 10, 20 centimeters around the antenna that is still sensed. So if you have a particle flying by the antenna, it doesn't have to hit the antenna. If you look with a laser, you look at a very, very tiny particle. Both particles have to appear on both lasers. The particle has to appear on laser 1, laser 2. And if it's not going through the laser light, then it can't be seen. Whereas a charged air cloud can hit sensor 1, and it can only hit sensor 2 partially. It can be a little bit offset. It doesn't have to be aligned perfectly. It still will be seen. And statistically, that is enough to make a good match between the two signals. So I think the answer to this is, if you're doing cross-correlation, the space discrimination of your measurement principle is very important, and also the distance. We cannot put our sensors 1 millimeter apart. We wouldn't see any correlation. It would be the same thing. So you really have to understand what kind of turbulence and what kind of flow you want to measure. And through our 30 years that we have been around, we have understood that, I think, pretty well.
Mm-hmm. Mm-hmm. Can we consider this measurement for performance guarantee test? And this is coming from a questioner in India.
We have done large performance tests in a project in South America for a very large power company in Europe, EDF, and they have relied on our measurement on the inlet side of the boiler, so airflow into the boiler, as well as on the flue gas outlet of the boiler. I have some reference letters I could send for that. So yes, the answer is yes, we have done complete performance tests. Now with performance tests, I'm sure the customer or the gentleman asking this question, we all know performance tests on boilers are a monster if you go for absolute numbers. If you do performance tests from one state to the other, so you do just a delta of the, it's much, much easier. And if you have good airflow and gas flow measurement, usually it's very well possible to prove a performance increase or decrease on boilers just with our gas flow measurement. And of course, the typical other measurements you have to take, temperature, O2, moisture of the gas, blah, blah, blah.
Okay, great. So let's wind this off with, we had one questioner who had more than 10 questions. So a lot of it probably has been answered during the presentation, but I'm going to just summarize all his questions, and if there are any areas that you have not touched on, you should probably just highlight, and if you have, then we can move on. And before I ask that question, there are some energy companies who have asked us about demos and pilot tests and so on. So we will get back to you on that separately. We have noted your request, and we will separately get back to you via email and schedule a time for a presentation. And feel free to also use the widget to request a specific time slot if you'd like to organize a one-on-one with us. So let's get back to this questioner's questions. And I'm just going to summarize it, and if there are any areas that you want to just touch on or reinforce, please do so, and if we have touched on it, then we can move on. For MECON digital airflow measurement, can it be used on PA, OFA, and SOFA lines as well as CFB, as well as on CFB with combustor flue gas at around 900 C? How sensitive is it to low gas velocities and temperature, and at what straight duct length is required to achieve accurate measurements? So a lot of this has been addressed, but if there is any final points you want to talk about, Hans, please do so. Yeah.
No, I think this really pretty much summarizes it. I think the questions coming from the audience were really, all of them, really good questions, critical questions. No, I'll be happy to talk to anyone who wants to have a video conference with us, talk about his application, his problems. We'll be happy to talk. Thank you all.
Yeah, perfect. So that brings us to the end of today's session. We had a number of questions, and we also have several that we had over close to 60 questions. So several of them have been repetitive, so we did not perhaps touch it, but we will be getting back to you, each one of you, to see if any follow-up discussions are required. So that brings us to the end of today's session. On behalf of PROMECON and Krishnan & Associates, I'd like to thank Hans for this excellent presentation and for sharing the expertise and his over 30 plus years of real-world perspectives. A special thanks to Luke as well, our producer behind the scenes, for managing today's broadcast, and to all of you for taking some time to join us. KNA produces a number of webcasts, and you can reach out on our website to learn about many different topics and several past PROMECON presentations as well. As a reminder, a recording of this webinar will be available on demand. Some of you have asked for a copy of the presentation. We can certainly send that to you, but please feel free to share this link with other people within your company. The same link that you use for registration should also work for on demand. You can just go in, punch in your credentials, and listen to it again. If you have any additional questions or would like to learn more about PROMECON solutions, please don't hesitate to reach out. Thank you again for being with us today, and we look forward to seeing you at our next session. Have a great day, everyone. Thank you.